Hi students, welcome to Year 11 Earth and Environmental Science, and this is Module 1, Earth's Resources. We're up to video number 6, and in this video we're going to have a bit of a look at the layers of the Earth. Now we've started to already look at some of the formation of the Earth and some of the evidence that we have for our interpretation of the Earth as having different layers. So what we want you to do in this particular area is to describe the compositional layers and thickness of the Earth's layers, including the crust, the mantle and the core, and their compositional layers. Now these sort of dot points can seem a little on the silly side because it's kind of repetitious, but that's one of the things that we need to look at when we're breaking some of these key areas down into subsections. So let's do that now. 3 areas that you can look at to see if you've been successful in being able to solve this particular learning goal, or at least to express your understanding, and that is to list the composition and relative thickness of the different layers of the Earth, to construct a model to represent the different regions within the Earth, and to evaluate the efficacy of a model of the Earth in terms of compositional layers and respective thicknesses. So there's going to be a little bit in this particular video on modelling. So the first thing we need to do is to have a quick look at scientific models. Now scientific models are ones that we build a lot in science, and generally speaking we build models for the very big or the very small. So where things are too small for us to actually see them and interact with them in a meaningful way, we build models to represent them. So we've done that with cells, we've done that with atoms, we've done that with molecules, and we've done that to try and understand how each of things behave. And of course our models need to be explanatory. They need to be able to help us to simplify or visualize complex phenomena or processes in a more simple 3-dimensional, sometimes even 2-dimensional, which can be a simplistic kind of way. What we want our models to do is to be able to respond in some sort of explanatory way to the data that we collect. So once we do collect some data, once we have some information or some evidence, then we need to put that with our model to either help us to develop our model or to help us critique our model. That is, does our model explain what we've seen, what we've observed and recorded, or does there need to be some change in the model? Models should be constantly tested in order to ensure that any data that is being collected continues to line up with what the model is expecting or predicting. And of course, models aren't just for the very small, they're for the very large as well. So we build models of the universe, of the solar system, and also models of our Earth. We can't see into the depths of the Earth, so what we want to be able to do is to build models that help us to understand the internal structure of the Earth. So I guess one of the things that we've been looking at in our formation of the Earth is this kind of difference between a planet and a planetesimal. So we had that sort of planetesimal accretion model of how these planets formed in the first place. So little tiny clumps clumping together to make bigger and bigger clumps. And the big difference, I guess, is the force of gravity being able to pull all of those things in tightly enough together to generate heat. So once a planet is large enough and the heat generated is high enough, then the liquid that's there can, I guess, be redistributed, moved around as a fluid, and then what will happen is that the denser material will sink to the bottom and the less dense material will rise to the top. And this is one of the things that is what we believe has happened. Obviously, the outside or the crust of any planet is likely to solidify first. It's the bit that's outside that heat source, so therefore it's going to cool quickest, and therefore it's going to turn from a liquid to a solid quickest. But what happens with these planets is that we've actually got a separation of distinct layers based on differences in density, and we'll have a little bit of a look at that later on. This gravitational distribution only occurs if a lump is large enough, a planetesimal if you like, is large enough to actually go through this redistribution of its materials. And when that happens, we can get these kind of distinct layers starting to separate out, and it helps us to identify the distinct layers that occur. Now again, we can't see them, so some of what we've had to do is to put together some of the evidence that we've looked at up to this point, some of the seismic evidence, some of the meteorite evidence, in order to help us understand exactly what's going on in these different layers in the Earth. So let's look at these three layers, and I guess I'm going to put the outer and the inner core together as part of the core, so that's why I've called them three layers, although we generally speaking do talk about four. The crust itself is kind of two different types of things. It is ocean crust, primarily ocean floor, and continental crust. One of the things that's interesting is that the ocean floor is very young. There's no ocean floor that's more than about 200, 250 million years old. The ocean floor, we are aware, is being replaced constantly. We've got these mid-ocean ridges, and we'll look at this more when we look at plate tectonics later on. But that's coming and creating new ocean floor. Now, it can't just keep creating, otherwise the Earth would blow up like a balloon, and that would interfere with our orbit around the sun. So as new material is added to create new crust, material somewhere else on the Earth is being lost from the crust back into the mantle. It's being subducted, in fact, back into the mantle. So new crust in some places and the older crust disappearing in others. That's what we find in the ocean floor, but not on the continents. The continents are the lowest density, and therefore even when ocean and continental crust come together, the ocean crust goes under the continental crust. The continental crust is very low density, and it rises and sits above. And as a result of that, it's really only processes like volcanic activity, which is rare where the continent is stable tectonically, or processes of weathering and erosion, which are going to change any of the materials that are on the continental crust. It doesn't subduct in the same sort of way that oceanic crust does. Although we do find some folding occurring where continental crust is coming together, which we find as an example for the Asian and the Indian plates forming the Himalayas. The crust itself is primarily silica. It's very rich in silica, which is a network crystal made of silicon and oxygen. And the temperature range -30, very cold at the poles, to about +50 in the deserts. The mantle has a number of distinct levels that we can see. The lithosphere we've talked about, so that's the layer that includes both the crust and the uppermost part of the mantle. Underneath that is the asthenosphere, and we've used this term plastic to describe the asthenosphere. Now, the problem with describing something as plastic is it tends to bring to mind Glad wrap, the stuff you might wrap your sandwiches in, or the box that you might put them in, or the stuff that we put things in from the supermarket. That's not what we mean geologically speaking when we talk about plastics. What we mean is solids that can flow, that can kind of behave a little bit like a fluid, like a liquid or a gas. And so that's what we have in the asthenosphere. So it's hotter. It sits underneath that solid but brittle lithosphere. So the difference between the mantle, the asthenosphere and the lithosphere in the mantle is that the lithospheric region is very brittle. So the parts of that will break under tension or compression. They break, whereas the asthenosphere is more forgiving. It will flow. And that's where we think some of the convection currents that drive plate tectonics originate, or at least occur. They originate a little bit further down, but they manifest themselves in the asthenosphere, which is why these plates are kind of moving relative to one another. Underneath that layer of asthenosphere is the lower kind of rest of the mantle, and that is a more hotter and more brittle region as well. Still solid, but very, very hot solids now. And finally, the core. The outer core is very, very hot. Now we're getting to between 4,000 and 5,000 degrees C, so this is super, super hot. The outer core is liquid, and we know that the outer core and the inner core are both dominated by metallic substances, especially iron and nickel. And the liquid part, the outer core, is what we think, the presence of iron in that outer core is what we think is the source of the Earth's magnetic field. The inner core is under a huge amount of pressure, and we don't know a lot about it. We only know sort of what we get from our understanding of seismic waves traveling through the Earth. But we think that the pressures, the fact that it's so thick down to there, means that it behaves more like a solid. It's super, super hot, but its particles don't have anywhere to go. And of course, when we're talking about solids, liquids, and gases, we're actually talking about what's happening with the particles, whether they're free to move around, such as in a gas, whether they flow past one another, as they do in a liquid, or whether they're rigidly held, as they are in a solid. So even if they have very high energy and are capable of motion, relative to other particles, if they're being squeezed super tightly together so they can't move, then they behave like a solid, and that's why we describe the inner core as a solid. So here are these kind of three main layers, four if you want to look at the separation between the outer and the inner core, which given one behaves as a liquid and one as a solid is probably right. But then how many different layers you want to talk about in the mantle too can really expand our understanding of these different layers within the Earth. So it's important to have a good understanding of each of these important Earth layers, their relative thicknesses, and some of the materials that dominate in terms of their composition. Thanks for watching.